morning, friends. I am here again for my course Aircraft Systems. Today I am in lecture number 16. My topic of the day is Icing and De-icing System. As you know, my name is Dr. Dwivedhi, Professor from Institute of Aeronautical Engineering, Hyderabad, India. As of now, I am in the process of running module 2, the vehicle system. In this, I have already covered the electrical system. I have covered the different types of electrical system. I have covered the DC system, AC system, air conditioning system, oxygen system and all. And in my unit 1, I have covered the airframe system, then vehicle system, avionics system and the mission system. And we have seen that how the progress is taking place from one system to another system. And we are here now today in icing and de-icing. So we can see that how ice is formed and how we can make sure that ice is removed. First of all, ice should not form, and if form, how the ice is removed. So this removal system is called the de-icing, and if we make a prevention of icing, it is called the anti-icing. So in today's my topic of the day, I will go with the revision of oxygen system, which you know that my previous class I have taken the oxygen system. In that I have explained types of oxygen systems and how it is working and all. Then I will go to the introduction to de-icing and anti-icing system. Then types of de-icing system. In that we have thermal pneumatic anti-icing of wing, thermal electric anti-icing, and then chemical anti-icing system. Just a little brief I have given in my previous class also about this anti-icing and de-icing system. And here I will go with full detail and how these things are working. So first I will go for the revision of the oxygen system. And as you know that I have discussed in my previous class that why we need the oxygen. Oxygen is very, very important. Without oxygen, a human or any living being cannot be survived. So, and a sufficient amount of oxygen with a certain amount of pressure is also required. If oxygen is there and pressure is not sufficient, or the quantity of oxygen is less or more, both are not good. So we have to make sure that a sufficient amount of oxygen for every crew should get. As we go up and up and up, we see that the density of the air is tremendously reduced. The amount of oxygen which is present in the air is also very much reduced. So the pressure and the oxygen amount, as you go higher altitude, you will feel that there is a lack of oxygen and the lack of pressure. The unconsciousness, giddiness of the people will feel. Also some people feel some vomiting type of experience and so many other parameters. And if it is very less, then a very high cases, a very serious problem can also happen. So we should make sure that the oxygen supply of the aircraft should be proper as per the given standard and as per given temperature and the pressure. Every person should get the sufficient amount of oxygen. So how we can get this oxygen? That is we have to discuss, and I will just give a glance on this. Then I will go, the next is introduction to de-icing and anti-icing system. Then types of de-icing systems, thermal pneumatic anti-icing of the wing, thermal electric anti-icing, chemical anti-icing system, and so on. I will be working on this. So now electrical power system, air conditioning system and the oxygen system. We have already done with the electrical system, and we have seen that different electrical system, that is AC system and DC system. And in this we have different voltage and different frequencies. Normally we use the 400 Hertz, 115 volt AC. Here we use 28 volt DC, or nowadays we are using 270 volt DC. So like this power we are using, and I will discuss about this air conditioning and the oxygen system in a brief before I go for the icing and de-icing system. So here we can see here, and I have explained this thing earlier also. Here ambient air is flowing as the aircraft is moving from one side to another side like this. The air is entering, and here we have the little pressure is increased here, and this air is called the ram air. This ram air is having some percentage, some 15 to 20% higher than the ambient pressure, and this higher pressure is tapped inside this, and it is going to the heat exchanger, and from here the ram air is entering to the main compressor, and here a high temperature and high pressure air is taken, trapped from here, and some percentage of air is coming for the your air conditioning purpose, and the remaining amount is going, some 90% is going for the combustion. Here the fuel is injected, and this high pressure from the compressor is entering here, and this with the some system we are injecting some fuel, and this high pressure and high temperature gases are generated. These high pressure and high temperature gases are entering in the turbine, and here expansion is taking place, and this expansion is making sure that the aircraft is, this gas turbine engine is totally working here. So now if you see here, from here to here, this high pressure which is trapped from the high pressure compressor is entering in the heat exchanger, and this cooling air is coming in this direction, and this high pressure is going in this direction. So this making that this things somewhat cooled, and the pressure is remained same. So this high pressure and medium cooled air is entering into the cooling turbine. This here expansion is taking place. Due to this expansion of this air, the cooling of the air will be done, and this cooled air is supplied to the cabin for the pilot, for the air crew, and for the passenger of the aircraft. And the work which is extracted from this high pressure air, this work is used to operate this fan, and this fan is working like an exhaust fan, and it is making sure that this flow of this cooling air which is used for the heat exchanger is done sufficiently. Here we can see that here 1 to 2 is a ram effect. Here is the main compressor. Then here we have the heat exchanger. This is the heat exchanger, and here we have the turbine. So this I have shown here, and if you see this 2 prime, 3 prime, they are the ideal cases. All the dotted lines are the ideal cases. These lines are the ideal cases, and the firm line are the real cases. Okay, so this we have to ensure that. Now I will talk about the typical continuous flow oxygen system, and we can see here that the charging is done, charging connection, and it is done from the external source. The external source may be O2 truck, which is having number of cylinders of O2. Okay, so one hose is coming, and this hose is connected here, and then it is opened here, and this will go to the charging valve. So this charging valve will be opened, then it will go to the filter. From the filter it will go to the non-return valve or check valve. This will permit only one directional of this thing. It will go from this side, but it will not allow from this side. Okay, and then it will go to the shut-off valve. From the shut-off valve we can select that we can charge the oxygen cylinder which is available inside the aircraft, and also we can make sure that if you are making this thing open, it will go to the filter. From the filter, it will go to the pressure gauge. From the pressure gauge, it will go to the pressure reducer. And from the pressure reducer, it will go to the pressure relief valve. So if in the pressure regulator, if the pressure is more than the required, it will be relief and it will be blown off. And here is the green blowout disc, and it will show if it is pressure is relieved, a disc will be red color will be appear. Normally it will be green, but as and when it is relief, here a red color will be shown. From this pressure regulator valve, it goes to the distribution system, and in the distribution system you can see that there are number of masks. They are calibrated orifices. We have the mask outlet, calibrated orifices are there. Then mask outlet, and there are a number of outlets are visible. Next is the demand flow system. In this demand flow, as and when we require the oxygen, that much amount of oxygen will be supplied. So when oxygen is delivered only as the user inhales, during inhaling of the user only it will go inside. As you breathe in, it will go. But as you go out, you exhale, the valve will be closed and it will not, oxygen supply will not be there. During the hold and exhalation period of breathing, the oxygen supply is stopped. Thus, the duration of the oxygen supply is prolonged. So the benefit of this thing, the duration of O2 supply will be more. That is the benefit of this type of system. And here the duration of oxygen supply is prolonged as none is wasted. It is not wasted. The oxygen is not wasted. Demand flow systems are used most frequently by the crew on high performance and air transport category aircraft. So this you can see here, that here is the co-pilot and this is the pilot. Here we have the observer, here we have the observer, and here we have the cylinder. From this cylinder, your oxygen is coming to all these people and they all are having their own mask. As per this inhaling, it will go, and as and when they are exhaling, your oxygen supply will be shut off and you will be able to sustain for a long time by the given amount of oxygen cylinder. So that is the benefit of this, and this type of things are mostly used for the military aircraft, and very few passenger transport aircrafts are used for this system. Now I will talk about the anti-icing system. So this anti-icing, it is a prevention of the formation of the ice on a surface, and de-icing is the removal of ice that has formed on the surface. So anti-icing is a preventive measures and de-icing is the curing method. So ice on the propeller blade or wings changes its airfoil shape and decreases the thrust it produces. Though rare to minimal, it can also create an unbalanced condition which produces a vibration that can damage the engine as well as the airframe. So if the weight is not properly, a vibration can take place and your aircraft may have some problems. Negative effect of ice building. So if ice buildings are formed, this you can see in this diagram. This is the aircraft and a huge amount of here, huge amount, this all ice is formed, and this you can see they are not smooth, they are very rough here. Okay, so it will have a lot of problems. So negative effect, destroyed smooth flow of air wing, leading to severe decrease in lift and increase in drag forces, can change pitching moment. As angle of attack is increased to compensate for decreased lift, more accumulation can occur on lower wing surface. Causes damage to external equipment such as antenna and can clog inlet and cause impact damage to fuselage and the engine. So it can also clog your measuring equipments like pitot tube, your angle of attack indicator, and these all air systems also can be clogged. Considering a cumulative hazard, because as ice build up on the wing, it increasingly changes the flight characteristics. So this you can see here that in this diagram, as this ice is formed here and here, the flight characteristics like lift, drag, pitching moment will change. Okay, so these are the effect of this. Types of ice, if you see, we have the types of ice. We have rime, has a rough milky white appearance and generally follow the surface closely. It is called the rime. Next is the clear and glaze, sometimes clear and smooth, but usually contains some air pockets that results in a lumpy, translucent appearance, denser, harder, and the more difficult to break than rime ice. And third one is the mixed one. It is the rime and the glaze. Both are mixed. So this you can see here the rime, then here this one, and this is the third. Ice detection. How to detect? So detection is very important. Otherwise, how you can do the anti-icing or the de-icing? So we have to detect. Electronic ice detection common, but can give false reading. Because this electronic ice detection is not good, it can give some false reading. GM is developing a mass-based ice detection system where ice builds up on external probe. After mass of probe has increased due to additional ice, anti-icing systems are alerted and turned on. This increases fuel efficiency and system life, as de-icing systems are only turned on as required by the condition. Types of ice removal. First we will do the anti-icing. Preemptive, turned on before the flight enters icing condition. So preemptive, it is turned on before the flight enters the icing condition. Includes thermal heat, propeller heat, pitot heat, fuel vent heat, windshield heat, and fluid surface de-icer. So it is called the anti-icing. Now de-icing is what? Reactive. De-icing is reactive, means after happening you react it. Used after there has been significant ice buildup. Includes surface de-icing equipment such as boots, weeping wings, systems, and heated wing. So now propeller anti-icer. Propeller anti-icers are ice usually appears on propeller before it forms on the wing. So first it will appear on the propeller. Can be treated with chemical from slinger rings on the prop hub. Graphite electric resistance heaters on leading edge of the blade can also be used. So in this we will use in this graphite heaters are used. Very light graphite heater. It is a carbon like of this thing, and first formation of it is called the propeller slinger ring. Propeller slinger ring. Okay, so these things are used. Now propeller anti-icer. So how this propeller anti-icing is done? The earliest propeller ice control, a system that is still in use, is chemical anti-icing. Isopropylene alcohol is carried in a tank in the aircraft, and when icing conditions are anticipated, some of it pumped into a cylinder ring around the propeller hub. The ring supply tubes delivers the alcohol to the propeller leading edge by centrifugal force, and grooved de-icer boots help carry it out of the length of the blades. So these are the systems, and this in a tank we are carrying, and here the propeller pump is there to windshield, to carburetors, to pump, and from here it goes to the propeller pump, and it will give to the here at the ring, and due to the rotation it will be sprayed inside in the zone. So this alcohol will help to prevent the ice formation. Nextly, windshield anti-icer usually uses resistance heat to clear windshield or chemical spray while on the ground. Liquids used include ethyl glycol, propyl glycol, grade B isopropylene alcohol, urea, sodium acetate, potassium acetate, sodium formate, and the chloride salts. Chemicals are often bad for the environment, so we should try to avoid the use of the chemical. Now we use another method is the thermal heating. We heat by the taking the heat from the engine, from the turbine side. So air heated, the bleed air from the engine heat inlet cowls to keep ice from forming. Bleed air can be ducted to wings to heat wing surface as well. Ice can also build up within engine, so shut-off valve need to be incorporated in design, usually used to protect leading edge slat and engine inlet cowl. Next is resistance heater, used to prevent ice from forming on pitot tube, stall vanes, temperature probes, and drain mask. So this we have to make sure that these things are prevented. So resistance heater, it is electrically operated. So it okay, this is the resistance. So here we give the power. So here heat will be generated, and this heater is fixed like this, the pitot tube. So outside we will put like this, and so this probe will be heated. So this hole is not clogged, not to clog. Okay, so that is the purpose of the used to prevent ice from forming on pitot tube, stall vanes, temperature probes, and drain masks. This we can see one diagram here. So how these things are going from here. Heat is from engine, hot air is coming, and this is injecting here. This will go here, and this will go, and it will go out from this hole. So like this, this is the total leading edge. Okay, and same way here for the wing also, a series of nozzles are here, and they are spraying here the hot gases, so that this leading edge space, these things are prevented from forming the ice. Now there are boots, inflatable rubber strips that run along the leading edge of the wing and tail surfaces. So this whole leading edge, a boots is there. When inflated, they expand, knocking ice off of wing surface. After ice has been removed, suction is applied to boots, returning them to the original shape for normal flight, usually used on a smaller planes. So these type of systems are used for the smaller planes, and they are spreading by the pressure of air. So these boots are expanding. So your ice is cracked and it will fall down. Next is called the weeping of the wing. So wing also weep like human also weep. So this you can see here. If this ice is formed, so fluid is pumped through mesh screen on leading edge of the wing and the tail. So a chemical fluid is pumped, as I have shown earlier. Chemical is distributed over wings surface, and this chemical is making to melt the ice, and after this melting can also be used on a propeller blade and the windshield. So it is like a weeping. When the ice is melting, the wing look like weeping. Okay, shown here, it is tears are falling here, all the waters are falling, so it is given the name as a weeping. So weeping of the wing means it is a melting of the ice due to some chemical or some electrical method, and these drops are falling, water drops, and this is called the weeping of the wing. Now we have the electro impulse deicing. Another method of deicing is an electronic coil under the skin, includes strong eddy currents on the surface. This you can see here. Here is the actuator assembly, leading edge. So deliver mechanical impulse to the surface on which ice has formed. A strong opposing force formed between coil and the skin. Resulting acceleration shed ice from the surface. Can shed ice as thin as 0.05 inches. So a very small amount of ice, it can be detected and it can be removed. That is the electro impulse deicing. So we will give the electricity and some motion will be there. That motion will make sure that the ice is removed from the system. Typical anti-icing C-130 aircraft. Engine bleed air is used for anti-icing wing and impinges leading edge, radome and engine inlet air ducts. Electrical heat provides anti-icing for propeller, windshield and the pitot tube. Engine bleed air used to heat engine cowl inlets. If leak is detected in anti-ice duct, affected engine anti-ice valve close. Wing anti-icing system provides bleed air to 3 leading edge slats on each wing. Wing anti-ice is only available in flight. De-icing and anti-icing. Anti-icing, the prevention. Okay, so anti-icing means the prevention of ice buildup, and de-icing means the removal of ice buildup. So anti-icing means prevention and de-icing means removal or curing after it has happened. We know that one proverb that prevention is better than cure. So we should try to prevent that disease should not happen. Same thing. The anti-icing means we should try to prevent that ice should not form, and de-icing means if ice is already formed, how to remove. So that is the de-icing is found on flight surfaces. Pitot head keeps ice from forming or in an indirect sense removes ice from the pitot tube. Anti-icing equipment is designed to prevent the formation of ice, while de-icing equipment is designed to remove ice once it has formed. This system protects the leading edge of wing and tail surfaces, pitot and static port openings, fuel tank vents, stall warning devices, windshield and propeller blades. Here I am giving some thermal pneumatic anti-icing of the wing, and here I have given a black and white, but here I can see one more thing. Here just you can see there are 2 engines. From engine, this hot air from the combustion chamber, or after that before the engine turbine and the combustion chamber, some hot air is trapped. This air is entered here with certain amount of regulator or shut-off valve. If you open, it will go in this side. From here it will be distributed. Here is a 3.5 psi switch. So if this is the less, it will make this thing on, and from here it will go to this 350 degree Fahrenheit over temperature switch. Here these are the switch, and these are the 140 degree Fahrenheit operation switches. So here these are the more high temperature from here to here, and these are the small less temperature switches. Here we have overboard outlet here. Here we have the 212 volt, 12 degree Fahrenheit temperature switches. So different range of switches are there. 350, 212 and the 140 degree Fahrenheit switches are there. And as per this temperature, they will make the more or less amount of hot gases so that the ice will removed from the leading edge of the wing. A detailed analysis, this detailed sketch is shown here. Here you can see that there is a contour etched outer skin, this red one, and then we have the green color, and here this de-icing air is coming here, and this we can see here that a hot air is entering here, de-icing air duct, and from here air is entering and it is going to the different portion, and from here also this air is coming and going like this, and from here also air is going and it is exhaust is going to ambient. So like this air which is shown here, how these things are happening, it is shown in detail here, and how the system is operating, it is shown here. So that is the thermal pneumatic anti-icing of the wing. So in this pneumatic air and the thermal, the temperature of the hot gases are used. So it is called the thermo pneumatic anti-icing system. Here we have the thermoelectric anti-icing, especially for the props, angle of attack, measurement, pitot tube, left, right, okay, and P2, T2 probe here. So these all are done by thermoelectric anti-icing system. Here we have the left angle of attack sensor, left side of the aircraft. Here we have the true air temperature probe, and here we have the left ice detector. Here we have the left pitot probe. In this right side we have the right angle of attack sensor, right pitot probe. Then we have here right ice detector, center pitot probe. Okay, so like this you should, these all probes are used for different purposes to make sure that, and these all probes are done by Electro. Thermoelectric means the electric is making to generate the temperature. So one coil is used, and this resistance is making to heat, and all the probes, especially this pitot tube or the angle of attack sensors and all the things, they has to be made heat, so that during the flying the ice should not enter, and the hole which is very very small, it should not be clogged. So this is made hot. So if any case any ice formation is taking place, your system will make it melt, and your system will work properly and it will be safe. Now if you see the chemical anti-icing system, because we use the chemical for this purpose. So chemical anti-icing is used in some aircraft to anti-ice the leading edge of the wing, stabilizer, windshield and the propeller. So the windshield, the propellers, wing and all the things, if you see here, these are the porous panel on the vertical stabilizer. This is the vertical stabilizer, horizontal stabilizers are here. All are some porous panels are there, and this heat is supplied. This you can see blue is 3x16 OD nylon, 5x16 OD. These are the pipe size, 1x2 OD nylon, 3x16 OD stainless steel. So all this dotted line, wherever this dotted line, I am not able to see here. So these things are made, and different metering pumps are there. Here tank is there, high pressure switches are there, proportioning unit is there, filler is there, solenoid valve is there, low pressure switch is there, metering pump is there, wind seal pump is there, proportioning unit is there, porous panel on stabilizer. And so this all the stabilizer, horizontal stabilizer and vertical, they have some porous, means some holes are there. So your high pressure and high temperature air is pumped, and with high pressure, so your ice is removed in this way. So here some chemical compounds are sprayed with some pressure, and in this way the anti-icing and de-icing systems are performed. So I am at the end of my lecture, and these are the references which I have taken from the Moyer and the Seabridge aircraft systems, mechanical, electrical and avionics system, professional engineering Publishing Limited, London. Another book is Moyer and Seabridge, Design and Development of Aircraft Systems and Introduction, AIA Education Series, AIA, this is the 2004 edition. Here, if any questions, you are welcome to ask, and I am ending here. My email ID is yddwivedi@gmail.com. You are always welcome to ask the questions, if any, and it will be my pleasure to reply you, and hope you have understood the topics of aircraft systems and this thing. We have covered some topics, and please be tuned for the next lecture also. Please subscribe this channel, and if you like, please put the like button. Thank you very much for joining this class, and hope you have enjoyed this session. And we will see in our next class that how the flight control systems are working, how the hydraulic systems are working, and how these things are useful for the future of the aircraft. Thank you very much, and I am ending my session here.
Like, share and subscribe. Hit the bell icon for more updates.